The arrival suddenly of artificial intelligence in people's everyday lives has unsettled even those normally very bullish on new technologies. But what if the raw power of this technology could mean finding potential cures and treatments in weeks rather than years or decades? That's already happening. So let's find out more with, in Palo Alto, California, Daphne Koller, co-founder and CEO of the biotech company Insitro, and an adjunct professor of computer science and pathology at Stanford University. In Atlanta, Georgia, Anant Matabushi, professor of biomedical engineering at the Georgia Institute of Technology and Emory University. And here in our studio, Laura Rosella, professor and Canada Research Chair in Population Health Analytics at the University of Toronto and education lead at Temerty Centre for Artificial Intelligence Research and Education in Medicine. Welcome, Laura.
Thank you
in
so
studio,
much.
and to those on the line. So last month, more than 1,800 people signed a letter, including Elon Musk and Apple co-founder Steve Wozniak, calling for a 6-month pause on the development of AI. Laura, I'm going to start with you. Many are clearly concerned about the downside of AI, but how would you characterize the promise of AI in advancing science, especially in medicine and in healthcare?
Yeah, well, in science and in medicine, we use data for all of our tasks, to test hypotheses, to develop models, to make discoveries, to make predictions. And so AI and machine learning is helping us use more data we couldn't use before, much more quickly in a much more sophisticated way. So the idea is that we can actually take the promise of that new efficiency and new ability to look at new data, and that'll enhance the scientific work that we do faster and perhaps open up new avenues.
All right, same question to you, Anant. How would you characterize sort of the promise of AI in advancing the medical field?
Yeah, thank you, Jan. I think the opportunity is tremendous for AI in health and medicine, particularly when you think about some of the big challenges and problems that we face today, problems around health disparities, problems around global health, particularly in low and middle income countries, areas of the world where there is not a pathologist or a radiologist in the entire country. And that's where I see the big opportunity for artificial intelligence to really make a difference in those areas of the world that really are underserved and don't have access to medicine and healthcare, and AI really being that great leveler.
Daphne, is AI ushering in a new era of science?
I think it is because, as Laura said, we are in a world where we have the opportunity to collect a tremendous amount of data about human biology. And human biology is incredibly complicated, far too complicated for the human mind to fully understand. And many of the diseases that remain with unmet need today are probably not one disease, and we're probably not characterizing them correctly. Alzheimer's is not a single disease. And if we're able to collect enough data about human biology and use the power of machine learning and artificial intelligence to disentangle what we see there, maybe we can finally characterize the right subsets of patient population and find interventions that have a meaningful effect size. And that would be transformative.
With that, I want to look at some recent advancements in medicine using AI. Science Magazine's 2021 Breakthrough of the Year was powered by AI and its ability to predict protein structures in the body. Last month, researchers used artificial intelligence to detect Alzheimer's risk with over 90% accuracy, and earlier this year, researchers used AI to discover a potential new cancer drug in less than 30 days in what usually takes years or even decades. Laura, I'm going to come to you. Machine learning and AI have been around for a while. What is happening now that is enabling these breakthroughs? You sort of mentioned it a little bit off the top. Data.
Yeah, we have the data that we just did not have before. So the fundamental, mathematical basis of AI and machine learning has been around for a while, but we did not have the amount of data that we have now and the granularity of that data. And then we didn't have the computational ability to process that data. So theoretically, we could do this, but now we can actually practically do it. We have the horsepower behind it to actually make these discoveries happen. And that's been the biggest change.
This is something that we harp on here in this country, is that in Canada, we don't have a lot of data. Where are we getting our data from? Is this publicly sourced data? Where are we scouring for it?
Yeah, the data come from lots of different sources. So from the biological point of view, data can come from the cells and what we measure at the cellular level and the biological level. For data I work with on humans, we get it from interactions with the healthcare system. We're doing more and more surveys and detailed measurements. It can come from non-traditional sources like social media or our devices. And so it's actually coming from all these different places. I work with environmental data, so it's coming from the sensors that measure things in the environment, images in the environment. So it's not coming from one place, it's coming from many places. And it's very variable. That's the hardest part
I was
about
going to say, is
it.
there some biases to this with science? It's
Absolutely.
very methodical in terms of how we get our data. Is there bias in some of the data that we have?
Yes, there's a lot of bias, and this is the part that makes people probably the most uncomfortable. The data generating processes are non-random when we work with this data. I, as an epidemiologist, obsess with bias a lot. So we think carefully about what the biases are, how we can mitigate it against them, and of course, having more data, independent replication, making sure we're not just working in one center but multiple centers. These are some of the ways we overcome some of the biases.
All right, Anant, I want to come back to you. I want to go back to the recent advancement and sort of the excitement. What areas of research are you seeing the most exciting results using AI?
So I think that there's been a lot of progress around AI for diagnostics. I think there are something like 300 technologies that have now been approved by the FDA in the United States for primary diagnosis of multiple different indications. There's a lot happening in the realm of ophthalmology. There's work that's going on in the cardiology space. But looking forward, I think beyond disease diagnosis, I think the opportunity is tremendous when it comes to predicting outcome, when it comes to predicting therapeutic response. And I think that that's where I see the next frontier, where we, in the United States, for instance, 40% of the adult population is going to be diagnosed with some form of cancer in their lifetime. And the big question is, how do you manage these patients? We know that you can't be hitting all these patients up with aggressive treatments. I think a big question for us today is better management for patients with a disease. And I believe that the next frontier will be the use of AI to help in tailor the appropriate treatment strategies and management options for patients going forward.
Daphne, my natural follow-up is, how is AI changing the discovery of new drugs to treat said range of diseases?
So I think first and foremost is identification of the right patient population, because I think we have some really compelling treatments today, but when you apply them at the population level, you have some subset that responds and a very large number that do not. And for those that do not respond, you've basically introduced a tremendous amount of toxicity. You've prevented them from benefiting from a treatment that might actually help them. So I think disentangling the complexity of disease to understand what are the right population subsets so that you can create a therapeutic intervention with a meaningful effect size is a critical part of it. And then the next part is identifying intervenable causal nodes, that if you actually modulate those nodes, those proteins or other metabolites in the body, it will actually make a difference to that coherent group of patients. And we're seeing a tremendous amount of development on the drug discovery side in first deconvoluting the patient population, interrogating causality, and then figuring out how to construct chemical matter of whatever, whether it's a small molecule or a large molecule or a gene therapy that would actually make a meaningful difference in intervening at that node. So I think there is just progress all throughout that process that's happening and is being driven by AI.
Daphne, what have you come up with in terms of that research there?
So in our work, first of all, I want to return to Laura's point. We take very great care in how we collect and generate our data. So in addition to collecting data from human populations, we also have a cell factory that generates stem cells and from human-derived populations, patients, healthy controls, so that we can actually measure disease at the cellular level. And so we have done some really exciting work in various diseases in neuroscience as well as in oncology, and uncovered what we believe are a compelling new class of targets for genetic epilepsies, which is the first therapeutic area that we moved into, as well as in the domain of cancer, identified both new targets as well as, importantly, new patient populations for drugs that already exist, are quite safe, are effective, but are not deployed in the right patient populations. And so those are the fastest path to clinical impact for getting into patients, because the path of getting from a target to an approved drug is quite a long one. Working with an existing drug is sometimes a much faster path.
All right, Laura, I'm going to come to you. We're going to get granular in our research here. You used a machine learning model to analyze health data of 2.1 million people living in Ontario. What were you able to discover?
We were able to accurately predict who among that population would develop diabetes in the next 5 years, type 2 diabetes. And the idea behind it is if we understand who can develop type 2 diabetes, who is likely to, we can prevent it. Type 2 diabetes can be prevented. We have well-known interventions that can prevent the onset or delay the onset of type 2 diabetes. So if we know who's most at risk, we can target those interventions more appropriately.
How accurate can we get? Can we get to the individualness?
This is a good question. I mean, no model really gets to the individual level per se, because what machine learning does and what all of these models do is say someone that looks like this with these characteristics, on average, this is their likelihood of developing an outcome. So we can be very accurate for an individual, certainly, but every individual will have slight nuances for sure. But much more accurate than me just trying to guess, oh, yeah, you have 1, 2, or 3 risk factors, you're probably going to develop diabetes. We can then use hundreds of variables, much more nuanced information. We're going to get much closer to our ability to predict the fact that you will or will not develop diabetes.
All right, my next question, it's a dangerous one because we could get in the weeds here.
For sure.
But how were you able to do that exactly? Is there an example that we can sort of understand of how you were able to sort of hone in on people who were at higher risk?
Yeah, I mean, so simplistically, the way these models work is they go through all these variables and they lump together characteristics that are most likely appearing in individuals that do develop diabetes and do not, and they essentially sort through and trying to identify common patterns between those individuals. It's a lot more complicated than that, but we take in information on the history, past interactions with the health system, other conditions they might have, other risk factors, their age. And so putting all these things together, you can come up with a score to determine, based on all these factors put together, this person's likely to develop an outcome. And in this case, we know what we're trying to predict,
right,
which is type 2 diabetes. But sometimes these methods can be used where we don't know. We're just trying to group some groups together
right,
that might be more similar than others. And in that case, it's much more of a discovery angle, saying, we know there's some commonality here. We don't know yet what to do, but we can try things. And I think that's some of the work that you heard about.
Very interesting. All right, Anant, I'm going to talk to you about another disease, cancer. How have you been able to use AI to improve outcomes for people with cancer?
Yeah, thank you for that, Jan. So our group has been really interested in how we could use AI with routinely acquired data. So talking about radiologic scans, CT scans, MRI scans, but also pathology images, to be able to really figure out which of these patients has the more aggressive variant of the disease and therefore is going to benefit from more aggressive treatments like radiation or chemotherapy, vis-a-vis those patients where perhaps the disease is not quite as aggressive. And some of these patients might benefit from perhaps no chemotherapy or a lower dosage of radiation therapy, or in some cases, like in the case of prostate cancer, there are several men who might benefit from no intervention at all because we have a much less aggressive variant of the disease. And so there's a big opportunity that we're finding with AI, with machine learning, to be able to tease out patterns from these radiologic samples, images, from the pathology images, to be able to really help risk stratify those patients who need the more aggressive treatment regimens versus those patients who might benefit from a less aggressive variation of treatment strategies because they have a more indolent or less aggressive cancer.
Daphne, in your experience with drug discovery, to what extent is AI helping us discover things that human scientists could never discover?
So I would like to begin where Anant left off, which is with the incredible amount of information that exists in images such as histopathology and radiology. And in many of those cases, when we apply machine learning to those images, we uncover patient populations that humans would never have been able to identify. Subtle patterns within the histopathology images, which is an incredibly information-rich source, and also collected abundance abundantly because pretty much every solid cancer patient has a biopsy taken as part of the standard of care. And so we've been able to take those large populations within, say, breast cancer, within colorectal cancer, and identify patient subgroups where a particular gene seems to be driving the cancer in ways that are not necessarily the case for other patients that have what is labeled as the same cancer as part of their medical record. And that driver gene is now a novel cancer target, but importantly, neither the patient population nor the fact that that gene is driving the cancer would have been identified by a human pathologist because the patterns there are too subtle for a person to have necessarily picked up on. Now, what's interesting is that sometimes once we've discovered that, we've developed methods for visualization, for explainability, so that we can show the pathologist what it is that the cancer is picked up on. And that's important because it also allows us to gain confidence that what's been discovered is not artifactual, it's actually real. It's not some kind of a biases in the data, as Laura was alluding to earlier, but it also helps teach the pathologists something new about tumors and how the cancer is different in different populations. So it teaches us new biology at the same time that it uncovers potential new and impactful intervention nodes.
All right, with that, let's talk about some of the challenges here. And to get into that, I want to read a quote from Scientific American. AI is currently hampered by a lack of transparency. This lack of transparency has been nicknamed the black box problem because no one can see inside the network to explain its thought process. Not only does this opacity undermine trust in the results, it also limits how much neural networks can contribute to humans' scientific understanding of the world. First off, Laura, why can't we see into this black box?
Well, the black box is an issue, but I actually think we need to get much more specific about what we
Let's
need.
do it.
And Daphne alluded to this as well. So to me, there's at least three parts of the black box. There's interpretability. We need to know what's in these models. Explainability. How are the different components contributing to how the model makes decisions? And then there's transparency, which is a big one. I would say that's the one that's probably most problematic nowadays because it's done so variable. And that is the way the model is constructed needs to be very clear, clearly documented, standardized. It needs to be reproducible. Someone needs to be able to independently verify it. And so right now, none of those things are happening consistently, and all of that's contributing to the black box. And so once we do have those things in place, I think we'll feel a lot more comfortable. It's not as simple as, oh, I just need to look under the hood and see what's in the model and all is okay. All those aspects actually need to be working for us to feel more comfortable.
In terms of the black box and sort of AI's contribution, when a scientist goes in, are we getting a step-by-step in terms of how it got to that result?
Not consistently. And some of it we can't fully explain.
Right.
So some of it is something that, oh, this is new. This is a pattern I wasn't expecting. We haven't seen this before, which is not necessarily a problem, but it means it has to be verified. Someone else in another institution might want to verify that. We might want to check it. We might want to do further experimentation. So it's just a step one, but it's pretty complicated. It's not as simple as just saying, oh, these are the variables in the model and stopping there.
All right, we're going to pick up on that a little later, but I want to bring Daphne into this. How big of a challenge is the black box problem?
I think it both is and is not. So there's techniques that people have developed, including ourselves, to help people see into the black box and sort of interpret what it is that the computer is picking up on. And it's especially easy in the context of images because you can visualize different variables and what it is in the image space that give rise to different conclusions. And so that gives, I think, people a much greater sense of confidence about what is going on. I think the other aspect, which is important to emphasize in drug discovery specifically, is that where the hypothesis came from matters up to a point, but ultimately you're going to be subject to the same rigorous test that every other drug is subject to, which is a randomized clinical trial. And so in the same way that we don't necessarily ask people where a particular drug hypothesis came from when we go into the clinical trial phase, because we know that there is a sort of fundamental ground truth verification process, which is, does this work on a randomized case control population? And I think that's a really important component that gives us confidence in any drug that we put into a human.
And in general, if we can't understand or see how AI has arrived to some potential promising results, we throw the words of confidence and transparency. How can we trust those results?
Yeah, so thanks for that, Jay. And just to keep things interesting, I'm going to be a little contrarian and maybe disagree a little bit with Daphne there. So I can give a very specific example of where the black box really came back to hurt us. About 6 years ago, we were working on a project looking at the use of AI to predict heart failure from endomyocardial biopsies. And we trained a network. We were able to demonstrate from a single institution that this network was able to predict the risk of heart failure based on what the network had learned or what the black box had learned from these biopsy images. And we were stunned by the results. We actually showed in a paper that the black box outperformed cardiac pathologists by 25%. We were ecstatic. But the postscript to that story is that a few months later, we got another tranche of images from that same institution. And when we ran the network again, the performance fell from the 97% that we'd achieved on the first pass to a 75% result, which was more in line with what the pathologists had been getting. And we found out only after much interrogation that what had happened between the first tranche of images and the second tranche of images was that a remote software upgrade had been applied to the scanner that had been used to digitize the slides. And that very subtle change in the appearance of the images had perturbed the network enough that it had drastically changed its performance from the 97% to down to 75%. And so because of that experience, our group has really focused on very intentionally interpretable approaches. And while we talk about the promise of AI to discover things that we don't know, one of the things to consider in all of this is that there is a huge body of knowledge that has been amassed for many diseases over the course of decades and potentially hundreds of years. Let's take histopathology as one example that Daphne referenced as well. Pathologists have been looking at slides under a microscope for over 100 years. And there's a deep well of knowledge that we have about the kind of hallmarks and patterns that are associated with more aggressive and less aggressive disease. The challenge is that pathologists don't do a very good job in terms of reproducibly identifying these hallmarks. And that's where I think the AI can be so powerful, because if the AI could help identify in a reproducible fashion these patterns, these hallmarks, then we are able to have very intentionally interpretable AI from the get-go and can demonstrate its relevance for diagnosis, prognosis, and treatment response prediction.
Laura, I'm going to go to China. Yeah, Daphne, if you want to respond, yes.
I'd love to respond, if that's okay. So I completely agree that there is an incredible body of knowledge and that we should be mindful of that. But I think if we just focus on reproducibly and reliably doing what a pathologist can already do, we are missing an incredible opportunity to discover new concepts. And I will refer back to a paper that I wrote back in 2011, which was one of the first machine learning analyses of histopathology data, which basically discovered the importance of the tumor microenvironment to cancer prognosis at a time when we did not realize that as a community. So it was one of the first earliest harbingers of the importance of the tumor microenvironment, specifically because we did not restrict the model to trying to do something that replicated what pathologists are already doing. So that being said, I completely agree that this needs to be done with care. There needs to be replication, ideally across distinct hospitals, not just doing with verification within a single hospital system and a single scanner device, but really replication across ideally multiple cohorts. There needs to be an explainability component trying to help us understand what the machine is picking up on. And as I said, in the context of drug discovery, the ultimate proof is a randomized clinical trial, which is really hard to fake. So I think I agree that we need to do this with very great care, and that it's easy, especially with modern day machine learning, to fall into a trap of getting to ridiculously high performances that are not driven by anything that is biologically meaningful. Completely agree with that, but I don't want to throw out the baby with the bathwater in preventing the machine from identifying new and important insights that a person did not previously discover.
All right, moving on. Laura, we know AI can detect patterns and make predictions when it's got massive amounts of data. We know it's limited in sort of explaining why something is happening and what is causing it. Does this mean that AI will never replace human scientists? There's a fear out there with every industry, right?
Yeah.
That AI is coming for us. But
Yeah.
in this, with science, this is a different realm. But the amount of progress that's been made is quite tremendous.
Yeah, I don't think of the term replace when I think of AI. And lots of people go there right away. I always think of augmenting. And so I think it'll augment the work of scientists for sure. Causality and understanding why things happen is a great example. There are important parts of that process. It's a multi-step process and some pretty key steps that need to be taken to really understand why. And machine learning can play a role in some of those steps and actually can help us get to that more quickly. It can open us up our eyes to new possibilities that we weren't seeing before, but we still have to go through all the steps. So I don't see it replacing. I mean, I'm a little hesitant to make any predictions in this space given the progress we've seen in the past year even. But I see it much more as augmenting the work that scientists do and still making sure that we keep the rigor and the domain knowledge that we've amassed over the years in that process.
Anant, I want to get your take on that as well.
Yeah, so I think that these prophecies of doom are not new, right? So AI is going to take away the clinician's job. AI is going to replace the pathologist. AI is going to replace the radiologist. As a history buff, I've gone back and looked at some of the stories that came out 30 years ago in the context of digital mammography. When digital mammography came out in the late 80s or early 90s, and some initial image analysis machine learning companies were stood up to analyze digital mammography, you could see these prophecies of doom. You're not going to need radiologists anymore. You fast forward 3 decades on, we still have a paucity of radiologists. We have a shortage of pathologists. So I agree 100% that we really need to be thinking about augmentation. We need to be thinking about assisting. And I think that one of the things that's been said more recently about AI is that, yes, it is likely that in the next 5 to 10 years, the radiologist or the pathologist who is using AI might obviate the radiologist or pathologist who does not.
Daphne, could AI develop to the point where it can create its own genuine scientific understanding? I might be going a stretch here, but think like an AI Einstein.
Boy, I tend to be wary of predictions saying AI will never do X, Y, and Z, because in the past, whenever we have made such predictions, they have turned out to be, in many cases, false. So I don't know if never, but honestly, I tend to agree with Laura that scientific endeavor is one of the places where it's the ultimate creativity of the human mind, and it is certainly the case that a human can be hugely supercharged, if you will, by having access to the kind of interrogation tools that allow a human to extract patterns and insights from very large amounts of data, which the human mind will never be able to process. But I think that the partnership between the human and the computer is where we're going to see the greatest insights. Now, will a computer come up with insights on its own? Probably, but I still think that the greatest insights are going to come from that partnership.
All right, Laura, it's been said that when Einstein made his big breakthrough with relativity, only a handful of people in the world actually understood it. Could AI, or an AI Einstein, produce a scientific breakthrough that no human could understand?
So I think that an AI could generate a starting step of a discovery that we will eventually understand. So I think that signals will come up. Some of them will be false. Some of them will be because of a bias or a spurious finding, and we have to do a process to get there. And some of them truly will be new paths of understanding that we did not yet have. So I think it could start us on that path. And I'm confident, though, that eventually with the processes that we use in science, we will eventually understand. It might take us time, though. So it might be signaling us something that we don't yet understand, but I'm confident that we will be able to get there in time.
All right, we are going to leave it there. Daphne, Anant, Laura, thank you so much for joining us on the program. Very, very riveting stuff. Thank you so much.
Thank you.
Thank you.
Great.
The Agenda with Steve Paikin is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.